All right, let's go. Number 10. The Horizon Problem. In 1964, Arno Penzias and Robert Wilson were not doing cosmology. They were trying to clean a horn antenna at Bell Labs in Holmdel, New Jersey, chasing a persistent hiss that would not go away no matter where they pointed the dish. They checked the wiring, they evicted a pair of nesting pigeons and scrubbed the droppings. The hiss stayed. What they had found was the relic radiation of the universe at 380,000 years old. Standard physics gives one hard rule about that moment. No signal, no heat, no information can move faster than light. At the epoch when that radiation was released, the maximum distance any influence could have traveled was roughly 0.27 megaparsecs. Projected onto today's sky, that is a patch about 1 to 2 degrees wide. Thousands of such patches cover the sky. None of them could ever have touched. They are the same temperature. Not similar. The same. To 1 part in 100,000. John Mather and George Smoot's Cobferus instrument fixed the value at 2.725 Kelvin in 1992, with deviations at the level of 10 to the minus 5. Planck's 2018 release confirmed it to higher precision. Alan Guth gave the puzzle its name in his 1981 paper in Physical Review D, Volume 23, page 347. Every escape route has been tried. Prearranged initial conditions, which is not an explanation, but a decision to stop asking. A speed of light that was faster in the early universe. Proposed by John Moffat in 1993, and by Andreas Albrecht and Ju Muguejo in 1999, which demands new physics with no independent support anywhere else. Stephen Holland's and Robert Wald's 2002 alternative, which requires a quantum gravity cutoff nobody can specify. And inflation, which works, but only by requiring its own smooth starting patch, a point on a aegis. Paul Steinhardt and Abraham Loeb pressed hard in Physics Letters B, Volume 723 in 2013. Those photons are passing through your body right now, several hundred per cubic centimeter, arriving from opposite ends of the sky carrying identical temperatures. What agreement did they reach, and when, if nothing could ever pass between them? The second problem was noticed at the same time, and it is worse. Number 9. The flatness fine-tuning. In December 1979, Alan Guth was a 32-year-old postdoc with an expiring contract, working on magnetic monopolies in grand unified theories. Monopolies were his job. Cosmology was a side interest he had picked up from a Robert Dicke lecture at Cornell, in which Dicke mentioned, almost in passing, that the universe's density was strangely balanced. The Friedmann equations make that balance unstable. If the density parameter, omega, is even slightly above 1, gravity wins and the universe collapses. Slightly below, expansion runs away and nothing ever clumps. Omega does not sit still. Any deviation from exactly 1 grows with time, relentlessly. Like a pencil balanced on its tip. Run today's measurement backwards and the pencil has been balanced for 13.8 billion years. Robert Dicke and Jim Peebles laid this out formally in 1979 in the Einstein Centenary Survey edited by Hawking in Israel. The numbers are brutal. At 1 second after the Big Bang during nucleosynthesis, omega must have differed from 1 by less than 10 to the minus 16. Extrapolate to the Planck time and the required precision reaches roughly 1 part in 10 to the 62. Planck's 2018 measurement combined with baryon acoustic oscillation data gives curvature at 0.001 plus or minus 0.002. The proposed resolutions each fail differently. Anthropic selection explains nothing about mechanism. Philip Helbig argued in Monthly Notices in 2020 that the whole problem is an artifact of how you choose your measure, which is a serious objection that most cosmologists have not accepted and have not refuted. Cyclic models replace one tuning with another. Inflation flattens space beautifully. Then needs a sufficiently uniform patch to begin inflating, which is the original problem in new clothing. Change the 62nd decimal place of that number and there are no galaxies, no carbon, no stable chemistry, no observer to notice. Why should a quantity free to take any value have been set, at the beginning, to 62 decimal places of precision? Before asking what lies beyond the universe, it helps to know where our knowledge stops. Number 8. The wall at 46 billion light-years. In 2003, Richard Gott III, Mario Jury, and colleagues at Princeton set out to make a poster. Specifically, a single conformal map that could show the Kuiper Belt, the Sloan Digital Sky Survey galaxies, the quasars, and the microwave background on one page without distorting local shapes. It was a visualization exercise. A map, in the ordinary sense. The obvious expectation is that a 8-billion-year-old universe should be visible out to 13.8 billion light-years. Light has had that long to travel. That is the whole calculation. The number they published was 14.26 gigaparsecs, 46.5 billion light-years, in every direction. The paper appeared in the Astrophysical Journal, volume 624, page 463, in 2005. The extra distance comes from expansion, carrying the emitting matter away while its light was in transit. The observable universe is therefore a sphere roughly 93 billion light-years across. The largest thing they charted inside it, the Sloan Great Wall, runs 1.37 billion light-years end to end. The boundary cannot be pushed back. It is not a limit of aperture, or exposure time, or detector sensitivity. Larger telescopes gather older photons, not photons from beyond the horizon. Gravitational wave astronomy may eventually see past the last scattering surface, but not past the causal edge. Neutrino backgrounds face the same wall. Worse, accelerating expansion means the moving horizon is contracting, objects visible today will redshift out of contact permanently, and no future civilization will recover them. Everything humanity will ever measure, argue about, or name sits inside that sphere. It is not the universe. It is the part of the universe that happens to be in causal range of the particular atoms that became you. How large is the region you are permanently forbidden from checking? And who decided that number? Some cosmologists suspect that sphere might not be an edge at all, but a repeat. Number 7. The wrap-around universe. Neil Cornish, David Spergel, and Glenn Starkman were working on a methods problem in 1998. How do you test something usually dismissed as untestable? They wanted a statistical technique, published in Classical and Quantum Gravity, Volume 15, page 2657, that could detect the shape of space rather than merely its curvature. Geometry and topology are different things. A universe measured as flat can still be finite, in the same way the screen of an old arcade game is flat but wraps at the edges. If space is multiply connected, light leaving Earth in one direction eventually returns from behind, and the last scattering surface intersects itself. That intersection would appear as pairs of circles on the microwave sky with matching temperature patterns. 5 years later, someone found a reason to look seriously. Jean-Pierre Luminet, Jeffrey Weeks, Elaine Riazuelo. Roland Lehoucq and Jean-Philippe Uzan published in Nature, volume 425, page 593, in 2003. MAP had found the largest scale temperature correlations to be weaker than expected, as though the longest waves were missing. Their explanation: space is a Poincare dodecahedral space, finite, positively curved, with a density of about 1.013. The model predicted 6 pairs of matched circles at an angular radius near 35 degrees. Cornish, Spergel, Starkman, and Aichiro Komatsu ran the search and published the result in Physical Review Letters, volume 92, page 21302, in 2004. Nothing. Budavine Rukama's group reported a faint hint at 11 degrees. It was never confirmed. Ralph Arake's team found suggestive but inconclusive signals. Planck's 2013 topology analysis closed the door harder, excluding back-to-back circles above roughly 20 degrees radius and setting a lower bound on the fundamental domain of 13.2 gigaparsecs. The missing large angle correlation that started all of this is still there, still unexplained. If space wraps just outside our horizon, the universe is finite, and no measurement we can build will ever tell us. Even the question of whether space is finite has not stayed settled. Number 6. The curvature that refuses to vanish. Eleonora de Valentino, Alessandro Melchiori, and Joseph Silk were doing parameter bookkeeping. The Planck Legacy 2018 release had a known oddity. The amount of gravitational lensing imprinted in the small-scale power spectra came out larger than the standard model predicts. Their task was to check which parameter extensions absorbed the excess. Flat space is the foundation of concordance cosmology. Planck combined with baryon acoustic oscillations gives curvature at 0.001, plus or minus 0.002. Textbook flat. Every distance, every age estimate, every galaxy count assumes it. Using the Planck power spectra alone, the preferred value was negative. Closed, A-sphere. Their paper appeared in Nature Astronomy, Volume 4, pages 196 to 203. The curvature parameter came out at minus 0.044, with errors of plus 0.018 and minus 0.015, favoring a closed universe at more than 99% confidence. Will Handley at Cambridge reached a compatible conclusion independently in 2019, publishing under the title of Curvature Tension. The counter-arguments each cost something. The lensing reconstruction from Planck's 4-point function does not show the excess, which suggests a systematic, but nobody has identified it. Introducing a lensing amplitude nuisance parameter absorbs the anomaly by naming it rather than explaining it. Adding baryon acoustic oscillation data restores flatness, but De Valentino's group showed that this forces discordance into most of the local distance measurements instead. The tension does not disappear. It relocates. And underneath all of it sits an unfixable problem. No measurement of finite precision can ever distinguish exactly flat from very slightly curved. Infinity is not an observable. You live in either a finite universe or an infinite one, and the difference may be permanently undecidable. Whichever it is, the theory that fixed everything else predicts far more space than we can see. Number 5. The space inflation leaves behind. Guth's original mechanism had one job: take a small patch, expand it exponentially. And both the horizon problem and the flatness problem dissolve at once. André Linde in 1982 and Andreas Albrecht with Paul Steinhardt in Physical Review Letters, Volume 48, page 1220, repaired the version that would not exit cleanly. Nobody was trying to manufacture extra universe. The required amount of expansion is about 60 e-foldings, meaning the patch grows by a factor of e60 times over. 60 is the minimum needed to explain what we see. Nothing in the physics stops at 60. Realistic inflatant potentials generically produce far more, and the excess is not a small correction. It is exponential. If inflation ran for 100 e-folds rather than 60, the total universe exceeds the observable region by a factor of e to the 40th power in linear scale. Planck's 2018 constraints, with a spectral tilt of 0.965 plus or minus 0.04 and a tensor to scalar ratio below 0.06, are entirely consistent with the longer versions and cannot distinguish among them. Attempts to bound the duration have all stalled. There is no observable that records the pre-60 history. Inflation erases its own initial conditions by design. IJOS, Steinhardt and Loeb argued in 2013 that plateau potentials, the ones data now favors, make the required starting conditions less likely rather than more. Guth, David Kaiser, and Yasunori Nomura answered in Physics Letters B, Volume 733, page 112, in 2014. Arguing the criticism rests on assumptions about probability nobody can justify. Neither side has been refuted. Every star you can name, every galaxy ever catalogued, every atom in your body occupies a fraction of the real universe so small it does not round to a percentage. If most of what exists is unobservable in principle, what exactly is cosmology a science of? The mechanism has a further property nobody intended. Number 4. Inflation that never ends. Alexander Vilenkin was working on quantum tunneling in 1983, pursuing the question of whether a universe could originate from nothing at all through a de Sitter instanton. The eternity result was a byproduct of the calculation, not its purpose. Inflation is supposed to end. The inflating field rolls down its potential, reaches the bottom, and releases its energy as hot matter. Local physics resumes. Standard cosmology takes over. The field is quantum. It does not only roll down. In some regions it fluctuates upward, and those regions keep inflating while the surrounding space has already stopped. Vilenkin published this in Physical Review D, Volume 27, page 2848 in 1983. Lind's self-reproducing chaotic version followed in Physics Letters B, Volume 175, page 395 in 1986. Because inflating regions double in volume while non-inflating ones do not, inflation always occupies more space than it has vacated. Guth reviewed the consequences in the Journal of Physics A, Volume 40, page 6811, in 2007. It has a beginning, though. Arvind Borde, Guth, and Vilenkin proved in Physical Review Letters, Volume 90, page 1Phi1301, in 2003, that inflating spacetimes cannot be extended infinitely into the past. The consequence broke probability. To ask what a typical observer sees, you must count observers across an infinite ensemble, which requires a measure. The proper time measure produces the youngness paradox, in which almost everyone should have been born moments ago into a hot universe. The scale factor cutoff measure, developed by Andrea de Simone, Guth, Linde, Madhyar Nourbala, Michael Salem, and Vilenkin in Physical Review D, Volume 82, page 063520, avoids that but is chosen for convenience. Ken Olam argued in 2012 that no coherent measure exists at all. Your entire life, everything you remember, has a probability that cannot be defined until someone decides how to count infinity. If no measure is correct, on what basis does anyone claim our universe is likely? The other universes acquired a catalog before anyone could see one. Number 3. The landscape of 10 to the 500. Raphael Busso and Joseph Polchinski published a paper in 2000 attacking the cosmological constant problem. Their tool was flux quantization across the compact extra dimensions string theory requires. Shamit Khatru, Renata Kalosh, Andre Linde, and Sandip Trivedi followed in Physical Review D, Volume 68, page 04605 in 2003, constructing a stable vacuum with positive energy. Both teams were solving specific technical problems. String theory's founding promise was uniqueness. One consistent theory, one geometry for the hidden dimensions. One set of particle masses and coupling constants derived from first principles. Michael Douglas started counting the solutions. His paper in the Journal of High Energy Physics, Volume 2003, Issue 05, Article 046, followed by work with Sujay Ashok in Volume 2004, Issue 01, Article 060, produced estimates so large that 10 to the power of 500 became the emblematic figure. Leonard Susskind named the resulting structure the anthropic landscape in his 2003 preprint. Each vacuum carries different constants, different particle masses, different physics. The objections came fast and remain unresolved. Tom Banks, Michael Dine, and Eugene Gorbatov questioned in 2004 whether the landscape exists at all as a controlled construction. And Banks has argued the case repeatedly since. Susskind himself has described the constructed vacuum as improvised assemblies unlikely to be fundamental. The Swampland program tries to prove most of the landscape is inconsistent and is not converged. Nobody has computed our vacuum from the theory. Nobody has computed any vacuum uniquely. The mass of the electron, the strength of the strong force, the fact that carbon has a nucleus at all, become accidents of which valley our region happened to fall into. If the constants of your body were selected rather than derived, what is left for physics to explain? One team decided to stop arguing and go looking for a collision. Number 2. The Search for the Bruise. Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Haranya Paris had a methodological objective, not a discovery objective. Multiverse claims were being dismissed as unfalsifiable. They wanted to build a search algorithm rigorous enough that its null result would mean something, with blind selection built in so no one could accuse them of finding patterns after the fact. If our universe nucleated as a bubble inside an inflating false vacuum, it has neighbors. Bubbles expand. Neighbors collide. A collision within our past light cone would imprint a circular disk on the microwave background, with a temperature step across a sharp causal boundary. They ran it on the UMAP 7-year data. The algorithm flagged candidates. Full Bayesian model comparison did not support any of them. The results appeared in Physical Review Letters, Volume 107, page 071301, in 2011, with the full methodology in Physical Review D, Volume 84, page 043507. They constrained the average number of detectable collisions across the whole sky to fewer than 1.6 at 68% confidence. Jason McEwen and the same group improved the filters in Physical Review D, Volume 85, page 103502, in 2012. Stephen Osborne. Leonardo Senatori and Kendrick Smith ran an independent optimal analysis in 2013. The null result settles nothing, and everyone involved knows it. The expected collision rate depends on the false vacuum decay rate, which is unknown. Signatures could be too faint to separate from primordial noise. They could span the entire sky as a gradient no algorithm would flag. They could lie entirely outside our past light cone, in which case the evidence exists and is unreachable. There may be a scar overhead right now spanning 30 degrees of sky that your instruments read as ordinary noise. How would you distinguish a universe with no neighbors from one whose neighbors left marks you cannot resolve? There is one patch of sky that has resisted every explanation for 20 years. Number 1. The cold spot. Patricio Villalba and colleagues at Santander were running a routine check in 2004. MAP's first-year data needed testing for Gaussianity, which is standard quality control, the primordial fluctuations should be a random field, and wavelet analysis is a conventional way to confirm it. They were validating a dataset. Gaussian random fields have predictable extremes. You expect cold regions and hot regions, and their depth and size follow a distribution the standard model specifies precisely. The kurtosis of the wavelet coefficients spiked at a scale of about 300 arc-minutes in the southern sky. Marcos Cruz, Enrique Martinez Gonzalez, Villalba, and Laura Kane published the follow-up in monthly notices of the Royal Astronomical Society in 2005. The feature sits at galactic longitude 209 degrees, latitude minus 57 degrees. It spans roughly 5 degrees in radius, averages about 150 microkelvin colder than its surroundings, and its coldest subregion reaches near minus 350 microkelvin. Fewer than 0.2% of standard model Gaussian simulations produce anything comparable. The elimination has been exhaustive. Instrument error was excluded when Planck independently confirmed the feature in 2013. Galactic foreground contamination was excluded because the signal has no frequency dependence. A Sunyaev-Zeldovich shadow requires a massive foreground cluster, and there is none. Cruz and collaborators proposed a cosmic texture in 2007. No other probe has supported it. The Eridanus supervoid, mapped by Istvan Saputi's team in 2015 and revisited by Anders Kovsis using dark energy survey data in monthly notices, volume 510, page 260, is real but appears too shallow. And Rawari Mackenzie's 2017 analysis in volume 470, page 2328, argued directly against it. Dragan Huderer and Penji Zhang showed the statistical significance drops with a different filter, which weakens the case without erasing the object. The multiverse collision hypothesis remains formally listed among the candidate explanations, with the status recorded plainly, no evidence, highly speculative. That patch of sky is above your horizon for part of every day, and nobody on Earth can tell you what it is. 10 entries. Not one of them sits at the frontier of physics. The horizon problem, the flatness balance, the size of the observable sphere, the shape of space, the curvature of the whole, these are the foundations, the parts we tested hardest, the parts we teach first. The universe is not confused about what it is. It has been consistent the entire time. We are the ones holding a map that stops at the edge of the paper and insisting the world does too. If you want to see more videos like this, click the video on screen now.